Hey folks, Mud Duck Sharky here. Today I'm working on an amplifier project. Surprise, surprise. This one's really one of the simplest amplifier designs in existence. I mean, it doesn't get a whole lot simpler than this. Maybe functionally, if you want an amplifier and you want to amplify some radio frequencies, this layout is it's probably one of the simplest. Maybe there's something simpler out there, but this is basically it here. So this video is going to be about this amplifier. More so about this type of amplifier, how the components work together to make everything jive. It's not so much about how to build this, it's more of an educational video of how this works. Because a lot of the principles here apply to every other type of amplifier. You know, if you want to go with something bigger, maybe a push-pull design, or cascading multiple push-pull designs into a larger system. Hopefully the breakdown of this really basic circuit will help you understand that even better. But first let me explain why I built this. So the reason that I built this is because I want to analyze different types of transistors, and I want to see what makes them happy, how much power they require, how much power they put out, and I want to do it one transistor at a time. I don't want to risk multiple transistors in a test circuit that may or may not fail. So I built this. If I pop one, it's no big deal to put a new one in there. I only waste one, and yeah, that's the reason I built it. So this thing has been around my my shack here for quite a while now, and I've put a lot of different transistors into it. I've changed all the different components multiple times. So please don't judge me on my soldering job, and don't judge me on how it's all pretty haphazardly thrown together, because it actually works pretty well, and it serves its purpose perfectly. So right now I've got a 2879C, little HG transistor in there, and so far this has been an interesting transistor. But let me show you some of the other stuff that I've had in there. I've had a Toshiba 2290 in there. I've had a 1446, and interestingly a 50 volt pill. What is that? MRF 448. This one put out a surprising amount of power. But like I said, that's why I built it, to try different transistors and experiment around. So let me fire it up and show you what it does, and then we'll talk about the theory, the schematic, the basics of the operation, and we'll go from there. So right now I've got my function generator plugged into my radio. So this is feeding audio, a sine wave, into the radio. That radio is going through this bird meter with a 10-watt slug. And after that, it's going into the input of the amplifier. The output of the amplifier is going into this line section here with a 250-watt slug. So that's what we're seeing here. I got a peak kit so we can see peak and average power. And then after that, it's going into my dummy load, but first through a sampler slug, so that we can see what's going on the oscilloscope. All right, let me check all my connections here, make sure I got everything buttoned up. All right. Guess I can go ahead and key the mic. So first thing I'm going to do is I'm just going to put a carrier into it, and we're going to see what we get. Okay, so I'm about pegging a 10-watt slug in forward. So let's check our reflect. Very little reflect power. So with that little tiny bit of reflect power, it's safe to say that this input tune is within, I don't know, 5 or 10% of where it needs to be. I apologize for the fans on the power supply, they annoy me too, but that's what I got to work with. So we're putting a 10-watt carrier into the amp, and on the output we're getting about 80 watts. A little over 80 watts, 8.2 watts. So that works out to a power gain of about 9 dB. It's pretty underwhelming. This is probably the lowest gain I've ever seen out of a single transistor. It's shockingly low power gain, actually. The 2290 has it smoked. You know, you put a couple watts into a 2290 and it's significantly higher. But I believe these transistors are different, and we're still learning about these, so I'll come back to that topic later. But we're putting 10 watts in, getting 70, 80 watts out. Now let's put some modulation in the station. I'm gonna modulate a 500 hertz tone onto that carrier. That's our tone there. So that's our average reading. You notice we're getting backswing. They call that backswing. So basically what's happening is I'm driving the amplifier into compression, and my peaks aren't turning out as high as they should be. It's just one of those effects of compression. So let's turn the peak kit on and see what we're getting for PEP. Helps if I turn the modulation on. So that's our carrier. That's our PEP there. Meter's reading about 130 watts, but in actuality I've found that this meter reads a little bit low. So it's probably in the 140, 150 range. Which is right on spec for the datasheet for this transistor. If you look up the datasheet for the transistor, the 2879C, actually there is no datasheet. You go to the website, it says 150 watts PEP. That's about what I'm getting out of it. And this radio is all I have. It's not all I have, but it's what I'm testing with right now, and it puts out about 30 PE. 30. Let's see what it puts out. Let's see what it puts out in PEP. Alright, so I got the 5x multiplier. Let's put it in peak mode. Okay, so in the ballpark of 30 peak watts is going into this, and we're getting 140, let's just say 140 out on the back end. That's not unreasonable. Like I said, that's pretty low power gain. Actually, it's surprisingly low for a transistor like this. I'm a little miffed, and I'm going to work on that anyway. But before we get into all that, let's just keep going here. So, as you can see, the amplifier works. Let me give you a quick walkthrough of what's going on this disaster zone of a circuit board here. So first of all, when I'm building stuff, I like to use SMA connectors because they're very cheap. And they're very cheap. The connectors for the coax is very cheap, so you can build a bunch of jumpers for almost no cost at all. If you wear one out, if you break one, it's no big deal. They have solder pins, so they solder directly to the board with no issues at all. If you want to do any kind of testing, you know, most of your test equipment that's in the affordable range is going to have an SMA connector on it. So SMA is really handy for that kind of stuff, but you don't want to put any real power into it. Maybe, I don't know what the rating is on these, but I probably wouldn't put more than a couple hundred watts through one. So anyway, our power's coming in here, and the first thing it's doing is going through a series capacitor. So I use this just to decouple the bias voltage from the RF signal. This is a very high value capacitor, so it's basically just a DC blocking capacitor. And on the other side of that capacitor, we've got an L network. So we've got a variable capacitor and an inductor. And that transforms our 50 ohm impedance down into the 1 to 2 ohm range that we need for the input of this transistor. So on the other side of the L network, we've got our choke. On this circuit right now, I am feeding in a little bit of bias current. So right now, we have no, there's a wire in the way. Right now I have no bias. Now I have some bias. So as it's resting with the bias turned on, the transistor is letting a little bit of current through. So we're letting about a half of amp through the transistor. That brings the operating point up. It increases the gain, and it actually makes it a little more linear, and has a few benefits to bias the amp. You know, Class C is good for some things, but biasing it like this, which would be Class AB, is good for some things as well. So basically for the bias, I've got a few volts coming in through this resistor here, and that's feeding into a diode, which is going to ground. So that just caps the voltage output at whatever the diode drop is here. A couple capacitors to make sure that AC doesn't get in there and do weird things, and then we've got a choke. So this choke just keeps the RF frequency from our input from going back into the bias circuit. Is that? Wow. Interesting. Don't judge me. It was working. I think I messed that up a few minutes ago. This resistor is just hanging out. It was part of a different circuit, so we can ignore that one. But that's the basics of the input side. We've got our input, a blocking capacitor, an L network, and a bias choke. And that's about it. If you wanted to operate this in Class C, you can take this end of the choke and put it straight to ground, and boom, you're in Class C. If you want bias, you just feed a little bit of current in here and bias up your transistor so that it's quiescently drawing a little bit of power, and boom, you're in Class B or Class AB or however much power you feed into it. I would strongly avoid staying away from Class A, especially for RF large signal applications. So that's the basics of our input circuit. Now, you might notice this resistor and capacitor. This is our feedback. So it's directly connected between, man, is that the drain or the source? I always get MOSFETs and transistors mixed up. The collector. So this is the collector. This is the base. We've got a series capacitor. This is a high value capacitor. It's just DC blocking because there's a high DC bias voltage here. So this capacitor just blocks the DC bias, and the resistor provides a little bit of negative feedback. So that helps to keep the amplifier stable. On the output side, we've got almost a mirror image of the input side, except for one thing: the power. So what this is just a choke. It's chokes the AC voltage from coming back through into our power supply. So this is our power wire coming in. There's a bypass capacitor there to help keep our DC voltage stable, a large one and a small one. And then that power goes through this choke, which is oversized, by the way. It just happens to be what I had. The power winds through that choke and it winds up over here. That's all there is to our choke feed. And then, like I said, the output is almost identical to the input. It's almost the same impedance even. This transistor just happens to be that way. So we've got our inductor and our capacitor. That's our L network. And then we've got our DC blocking capacitor that blocks the DC bias voltage from here and just keeps the DC voltage from going out through our dummy load. It's really, really simple. It's really very, very simple. So let's talk about how I calculated the values for the impedance and why I needed to do that. Okay, so if you're at all familiar with L networks, I suggest you continue to watch this video. If you don't know what an L network is, that might be something you want to research before watching this video any further. Basically, L networks just convert your impedance from one impedance to another. They allow you to match different things. L networks are really common in RF. They're kind of the basic building blocks of so many different devices. And this L network here it's just two components. It's a capacitor and an inductor, and it transforms our impedance from 50 ohms down to the 1 to 2 ohms range that this transistor requires. I don't know if 1 to 2 ohms is optimum for this transistor, but that's what's on the 2879 datasheet, so it's where I started, and it seems to be getting really great results. I didn't show it earlier, but the harmonic output of this amplifier it's spectacular. It's so clean. It's not even worth, like, you could seriously run this thing without a low pass filter and it would just be clean. It's amazing the simplicity of this design allows us to get such a clean output. But that's a tangent. Let me get back to the topic of impedance and impedance matching. So in order to figure out the value of this capacitor and this inductor, first I needed to know the input and output impedance of my transistor, and for that I referred to the 2879 datasheet by Toshiba. Unfortunately, I can't find a datasheet for the HG2879C. Go figure. Thanks, China. Make a product, no datasheet. Cool. So I went with the Toshiba datasheet and went with those impedances, which was, if I remember, about 1.5 ohms with a little bit of reactance. So I found those numbers, and then I went over to the computer and I punched in my calculator. Okay, I need to transform from 50 ohms down to 1.5 ohms with a little bit of reactance. And then it spit out a couple of values for a capacitor and inductor, and that's the basics of what I used. So I think it spit out about 600 picofarads for the capacitor and about 50 nanohenries for the inductor. So those are kind of the components I started with, 50 nanohenries and about 600 picofarads. So this capacitor is pretty widely adjustable. It goes from about 300 to 1400 puff, and it gives me a good adjustability range to fine tune this. More range than I'll need anyway. And almost the exact same thing is true on the output, because for this particular transistor on the Toshiba datasheet, the input and output impedance are almost identical, which is makes it really easy. It makes it really easy. So if you notice, these inductors are wound with pretty heavy gauge wire. The act of transforming the impedance from such a high value to such a low value can really waste a lot of power if you don't have high Q inductors and capacitors. These capacitors are pretty high Q. They can handle a ton of current. They're good for about 500 volts. This inductor, pretty large. It's more than adequate for the 30 watts I was putting into it earlier. On the output, I went with an even larger inductor wire. That's 1/8" copper tubing. And for this inductor, I think I ended up lower than 50 nanohenries. I think I ended up somewhere around the range of 35 to 40. And I think that's because there's some stray inductance here in the circuit itself. So same capacitor, fully adjustable. And my DC blocking capacitor, just a large value high voltage cap that can handle the RF power going through it. And Bob's your uncle. We're off to the races. So when I first fired this up, I had checked and measured the input and output impedance. So before I even put the transistor in there, what I did is I took my my Nano VNA and I built all my L networks on both sides, and I took an SMA connector and connected it up to where the transistor sits. We're going to do that in a moment, and I'll show you what the impedance is. But I took my Nano VNA, connected it up, and verified the impedance of these L networks. So when I first started, this impedance was actually a little high. It was about 2 to 2.5 ohms, and this calls for 1.5 ohms. So I fired it up and ran it, and it actually had reasonable results. It wasn't too far off from what I was expecting, but it wasn't quite right. It wasn't putting out the peak power that I was expecting. So I went in there, and all I had to do was, in this case, I changed one inductor. I lowered the value of that inductor, and that allowed me to tune my matching capacitor for a lower impedance. So if you notice, we have a really good input match on the input tune. That's really cool because I didn't have to change this inductor. I just calculated it, put it in there, checked it with the VNA. It was within 10 or 20% of where it needed to be, and off to the races. There we go. We got pretty good, pretty dang stinking good input match there. But yeah, that's the basic process of it. Let me pull this transistor out of there, and we will measure these L networks and see what they are. Alright, so I've got some little SMA connectors installed where our transistor is. So it's really hard to tell from here, but the center pin of these SMA connectors is connected where the transistor used to be, and the transistor is disconnected. I know it's really cramped in there, but trust me, the transistor is disconnected and the SMA connectors are in their place. So the ground of these SMAs is connected to the ground plane on the circuit board. So right now, we're taking a measurement backwards through the input network to see what the impedance is. In order for this to work, we have to put a dummy load where our radio would be. So this is where our radio would connect. Our radio would run into here, but we can't really measure the radio. I don't know if the radio is truly 50 ohms. So what I did is I put a 50 ohm termination on there, and it's basically just a 50 ohm resistor inside of a nice little SMA connector. So let's take a look at the Smith chart and see what we're getting. Let me get this in focus. Alright, so all the data we need is right here. You can see that we have a very, very low impedance just by where our icon is on the Smith chart. If you notice, there's our frequency. Haha, chicken band. In the upper right hand corner of the screen, I don't know if you guys can see it, but it says 1.33 ohms, J minus 0.122. So that happens to line up with the data sheet very closely. So just judging by our reflected power on the input circuit of this device, we can say that our input circuit is very, very closely tuned. We've got a fantastic SWR. We're putting 10 watts in. The meter is barely moving in the reverse direction. So our input tune is smack dab where it needs to be. Over here on the data sheet, if we scroll down the list, pretty much every... Yeah, my dog is over there drinking like a fish. Every data sheet's going to have a series impedance for the input and output, for RF transistors, that is. And of course, if there's no data sheet like HG over here, China, you're not going to have a data sheet at all. But this is the Toshiba data sheet. And this is our input impedance of what they recommend for the Toshiba 2879. 1.45 J minus 0.95. And over here we're getting, let me write it down for some clarity, 1.33 J minus 0.95. 0.1. So this is the impedance that we're getting measured through the circuit. I already measured the output, and it was very similar to this as well. So let me see if I can do this one-handed, because I'm too lazy to set up a real camera and a tripod, because I'm not a YouTuber. I just make videos about radio stuff because it's fun and interesting. And any day now I'm gonna have this connected. Are we there yet? We're there. Okay. Alright, so this is our output impedance. We're getting right about the same. 1.33 J minus the 0.3. Sorry if you can't read that, it's kind of tight up in there in the corner. But we're getting almost the exact same thing. 1.33 J minus 0.3. So that makes really good sense. That's perfect sense. So on the output side, I've got the same thing. I've got the output where your dummy load would be. Chicken band, dummy load. We don't transmit into antennas, we transmit into dummy loads, right? Right, boys? So this is where our dummy load would connect, but I've just got a pair of, I've got a 50 ohm resistor basically. It's just two surface mount 100 ohm resistors acting like a 50 ohm load for the purpose of measurement. So right now we're measuring the impedance that the output transistor is seeing, and this is what we're getting, which damn near nails the data sheet. And if you remember, I don't know if I talked about it earlier, but the way that I tuned this circuit is first I fired it up, I put a very low power signal into it with my radio, and I watched the reflect meter, and I adjusted this capacitor for the lowest possible reflect. It just so happened that I didn't have to do anything after that. You know, just I nailed this inductor on the first try. So I adjusted this capacitor, my reflect was negligible, everything was hunky-dory from there. For the output, I did exactly the same thing. So once I got my input roughly tuned, I turned up the power a little bit, and I tuned this instead of for the best reflect power, I tuned it for the maximum gain. So the most forward power output from the amplifier. And it was a little underwhelming. I cranked up the radio. Like I said, this transistor, it's really low gain. I have to put so much power into it, and I've got multiple of it, and I've verified with a push-pull setup that these transistors just require a lot of power to get anything out. And because of that, I'm not a huge fan. But anyway, I did the same thing here. So I tuned this capacitor for the maximum output power. And I knew that on my first go-around that my inductance was too high, because I connected an SMA connector and measured the impedance that I was able to get, and it happened to be too high. So if your output impedance is too high, your power output is going to be low. You're not going to be able to, you're not loading up the transistor enough for it to really make power output, given a maximum, a certain input voltage. So what I did is I made a smaller inductor, put it in its place, and repeated the process, tuned the capacitor for maximum output. And yeah, lo and behold, this is where we landed, which is pretty dang close to the data sheet. You know, I can't attest to the accuracy of this Nano VNA. It's pretty much the best tool I've got for this purpose. It's calibrated to read at the ends of these pieces of coax. I'm not going to get into using that. There's a lot of tricks to getting accurate measurements with a VNA. There's even more tricks to doing it with a crappy VNA. So we're going to assume these readings are fairly accurate, and it's all calibrated, everything's good to go. But yeah, that's basically what I did. So once I got to a satisfactory output power, something that I would expect, we'll go into that in a little bit later of how I knew how much power to expect from this device, and it wasn't the data sheet. I knew I was into the ballpark. So a higher impedance provides less power, a lower impedance provides more power, but it's more likely to overload your transistor. Surprise, surprise. So this seems to be around the magical zone, where actually, honestly, on the output impedance, I think we could go quite a bit lower. I think that this transistor has got the capability of going quite a bit lower, maybe into the 1 ohm, 0.9, 0.8 ohm range. At 14 volts, that is. You know, if you We could always put more volts into it and get more power out of it, and that would literally accomplish the same thing as decreasing the impedance. But this transistor can only handle so much voltage, so there's a limiting factor there. I've been running this at 14.4 with these impedance numbers, and you saw the results. Pretty low gain. Low gain, low gain. But anyway, so let's talk about the impedance numbers that are listed on the data sheet, because they can be fairly confusing. So you notice it says series equivalent input impedance. Now that doesn't give you all the information you need to know to actually build an amplifier. It gives you most of the information. But in order to know what these numbers mean, you have to know the standard for obtaining these numbers. And Motorola makes a wonderful data sheet or a wonderful application note about how these numbers are obtained. So if this is something that interests you, I strongly recommend reading that. I'll put that down into the notes of this video, the link to that data sheet, or that application note rather. And I'm just going to give you the cliff notes of that. So these numbers are obtained by building a test circuit, something like this. Almost exactly like what I've got going on here. That's their test circuit, by the way. That's how they obtain these impedance numbers. So these impedance numbers are obtained by building a test circuit, verifying the operation of the amplifier, and tuning the test circuit to their perfect ideal parameters that they want to see from their transistor. And then what they do is they pull the transistor out, and then they measure from here, and they measure from there. And those are the numbers that you get on your data sheet. So that's exactly what we're doing here, is we built a test circuit, we put a transistor in, we tuned it where we expect it to be, where we want it to be. Like I said, I could tune this for more power, I could tune it for less power, I could go easy on the transistor, I could push it harder. Motorola takes this, that's what we did here. We built a test circuit, we tuned it to our parameters, and then we went ahead and measured. So these numbers are their measurements of their test circuit. These measurements are not made on the transistor itself. These measurements are made on the test circuit in which the transistor was tested and in which these parameters were provided. So if we take a look up here, the Toshiba 2879 was spec'd at 100 watts PEP with a power gain of 13 decibels, blah, 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 blah. You know, the vast majority of this AC related data that's on this chart was obtained from this test circuit. And that's how they got those numbers. So when we're looking at those impedance numbers, I'm sorry if I'm droning on about this, but it's something that took me quite a while to understand, and I want to share it with you, is that this is not the impedance of the transistor, this is the impedance of the circuit, measured this way. So if we're measuring the input, we connect an SMA, and we measure backwards through the input, and we measure forwards through the output. So in all actuality, the impedance of the transistor has the opposite conjugate match to this. So if we want to say what's the impedance of this transistor, well, that's a complex topic. But basically, we could say that the transistor is 1.45 positive J1.0 on the output. And we could say that it's positive J whatever on the input. So yeah, just a interesting topic to go over. There's a whole lot of ground to cover there, and I strongly recommend researching it if amplifiers are your deal, like they are mine. I love playing with things that go boom sometimes. Anyway, so let's take a look at this test circuit. This test circuit is surprisingly similar to what I've got going on right here, except there's a few differences. Let's start with the input here. Alright, so this here is our transistor. And this whole side of the circuit is the input, this whole side of the circuit is the output. So the first thing that we encounter on the input is our 50 ohm input, and then that goes through a DC blocking capacitor. Now in their test circuit they had that variable for simplicity, and because I already had impedance numbers kind of dialed in for me, I don't need to have an adjustable capacitor here. It wasn't necessary in my opinion for this particular test. So basically I just omitted that variable and just put a high value capacitor in its place, simply to block the DC bias voltage. Alright, now the next thing that the RF encounters is a shunt capacitor. A shunt capacitor means from the signal to ground, and that's a variable, and that's exactly the same thing that we've got going on here. So we've got our series capacitor and then our shunt capacitor. and that one's variable. The next thing that the RF encounters is an inductor. Same thing here. We've got our inductor. So these three components right here are our L network, and then this, I don't know if there's a name for that, T network, I don't know. After the inductor, we've got a resistor and our RF choke, and then this whole section is our bias circuit. So this section provides a little bit of current into the base of the transistor to turn it on just a little bit when we're ready to put RF into the device. So turning on the transistor just a little bit has a few benefits, of which I'm not going to go into. If you want to research that a little bit more, look into Class A, Class B, Class AB, Class C, Class D, all the different classes of operation for a transistor. It's mind-numbingly boring, but it applies here. And then the next component that encounters is a resistor here. This is to shunt it to ground. I actually have this on the circuit board, but it wasn't connected. So this is a 100 ohm resistor, and I actually did a test with this connected to the base of the transistor, exactly how it is here. And it drastically improved my input reflect. So that little buffer there actually takes a little bit of the reactive inconsistency out of the circuit, and it makes it a little bit more stable as well. I left it disconnected because the transistor was providing a little bit more gain without that connected. But this isn't something that you want to plug in and run. This is just a test. That's why this is disconnected, because I was testing. You know, don't copy anything I did here and say, oh, my duck Sharky told me I could do it this way. Now this is experimentation, is all this is. So up in this area, this is almost the same as what we've got going on my test palette over here. So the broad strokes of it are: we've got our input, we've got our matching network, we've got our bias circuit, and then we've got our transistor. And that's all that's going on here. Super simple. Now let's take a look at the output. Oh no, you do. Oh no. Gotcha. Somebody's going to call an exterminator here in a few minutes. But anyway, let's take a look at our output circuit. So our output circuit is, for the most part, it's kind of a mirror image as far as the matching network goes. So we've got our inductor and our shunt capacitor. That's our L network. And then we've got our DC blocking capacitor, which in my case is a fixed capacitor of a high value, just to block the DC. But over here we've got our B plus, or our VCC, or our power input, or whatever you want to call it. And the circuit for that is beyond simple. I mean, it's just a couple of capacitors to keep the voltage stable, and a blocking capacitor. You know, not a blocking capacitor, a blocking inductor, choke. So that choke right there is my power choke right here. Again, this choke is exaggeratedly oversized, but you know, no kill like overkill. So the entire operation of the amplifier is pretty simple. Your signal comes in, the impedance gets transformed, and your AC current goes in and out of the base here. And that progressively turns your transistor on and off. And in the resting state, the collector of the transistor has a positive voltage on it. So as you turn this transistor on, it takes this point from your VCC voltage and it drops it down. Now the inductor slows down the flow of current a little bit, and it only lets a little bit through. So the first time you turn on this transistor, only a little bit of current's going to flow through. And then at that point, this voltage is changing. So that change in voltage, that signal, is making its way through your L network and to your output. So our transistor is turning on, pulling a little bit of current through. And then as this turns off, this inductor is pushing a little bit of current through. So this inductor is changing the voltage. This inductor is a key component in making this whole circuit work. Without this inductor, your transistor blows up. So our transistor turns on and our inductor lets a little bit of current through. Now the frequency that is coming through our transistor hopefully will be resonant with our matching network here. So this matching network is going to resonate at a certain frequency, and it's not going to resonate at other frequencies. So as this turns on, it's gonna start to resonate this network, and this network and the choke and the transistor all come together to form a resonating circuit that moves this voltage up and down at the frequency that you're inputting into the amplifier. And then that up and down motion, that up and down AC current is going to travel through here, get transformed into a different impedance. And Bob's your uncle, it goes out to your dummy load or whatever you're connected to, your alien spaceship, and you got some RF power. So the nuances of all of this stuff right here are many. There are many, many nuances to what's going on inside of an amplifier circuit like this. I'm not going to pretend like I can explain them all to you. I can't. I'm still somewhat of a novice at this, and I'm just sharing the basics. That's what I'm here to do today because I'm enjoying this project. It's been really fun to try different transistors and experiment with different things. And you know, I'm pretty underwhelmed with this HG2879C. I mean, I'm sure it can put out quite a bit of power, and I'm sure if I fed more power into it, it would do that. But as it stands, the gain is so low, you know, 9 decibels. When I mess with LDMOS devices, for example, I get 30 decibels of gain, which is, it's a pretty incredible amount of power. You know, you put 1 watt into the device and you get 1,000 watts out. That's 30 decibels. This is 9. You put 1 watt in, you get less than 10 watts out. So anyway, I'm probably going to turn this into a push-pull circuit. I'm going to take the data that I have learned here, and I am going to work on my chops. My radio frequency chops. I'm going to take the information that I've obtained here, and I'm going to apply it to a push-pull circuit, and I will certainly make a video on that once I feel confident explaining it to you folks. And yeah, in the meantime, I'm going to go back and I'm going to change this inductor, and I'm going to drop the impedance, and I'm probably going to push this transistor as hard as I can with a bigger input signal and collect some more data and see what the results are, and apply that to my future projects. But this has been a long video. If you made it to the end, I'm excited because that means that you're interested in this stuff, and I hope you learned something. And if I made any mistakes, feel free to correct me. I'm not a pro. I don't pretend to be. I'm just a hobbyist with a nano VNA, soldering iron, and a bunch of parts. But anyway, I'm Mud Duck Sharky. Thank you for watching, and I'll be back soon.